Hello and welcome. This is SFU Math 152, Calculus 2. My name is Brenda Davison. We are now at section 7.2, Trigonometric Integrals. So this is basically going to be some strategies for integrating trigonometric functions. So we'll basically be illustrating the variety of techniques with some examples. Okay, so here we are. We want to integrate sine squared of 3x. So one of the first things to occur to you when you see sine squared or cos squared is to use the appropriate identity, which in this case is going to be sine squared x equal to 1 minus cos 2x all over 2. So I'm going to replace that, use that identity to replace the integrand here, and then it will be 1 minus cosine of 6x divided by, because we have here 2 and here we have 1, so here we have 3, so here we have 6, 2x, like that. Again, and this becomes pretty trivial. That is going to be 1/2 x minus sine 6x over 6 plus the constant. Okay, so I guess strategy 1 is trig identities. I will give further direction about this closer to the exam. For the most part, I'm not going to require a huge lot of memorization on the trig identities. I may provide a table of them and say, you know, some of these might be useful, or I may make it such that it's only the most basic of identities that are needed. But one thing is, if they are basically in your brain, then you can they will occur to you when you need to use them. So you know, you may, I don't know, not be able to remember if that's a plus sign or a minus sign or something like that, but you should be thinking to yourself, oh, it's a sine squared or a cos squared. There's an identity that's going to help me deal with that. So that you want at least passing knowledge of them so that you can deal with it comes into your head about what to do. For example, we also have the other identity, cos squared x is 1 plus cos 2x over 2. So those are both extremely useful when we're doing the trigonometric integrals. Okay, next one, cotangent squared. Okay, so this one's not maybe quite as obvious, but we have I've done this before, but let me just do it again. This for sure, you need to know this identity. Sine squared theta plus cos squared theta is 1. That is a statement of the Pythagorean theorem in the unit circle. So we can divide both sides by cos squared. So I'm going to divide by cos squared, and that will get me the other identity, which is tan squared theta plus 1 equals secant squared. That's dividing through by cos squared, dividing this through by cos squared. I'm going to divide that same thing, that starred Pythagorean theorem, through by sine squared, and that is going to get me this one, 1 plus cotangent squared of theta is cosecant squared theta. Okay, so you don't have to memorize those ones. You can generate the other two from this one. I'm going to use that identity, this last one that I just regenerated for myself. I'm going to use that right here to rewrite this like this: cosecant squared of 3x minus 1 dx. So that's using the trig identity. Why did I do that? Because I know what the integral of cosecant squared is. That is cotangent. So then I can immediately write the answer here, minus cotangent 3x over 3 minus x plus c. Okay, so you need to be able to, this one here, inspection, you should check out page 471 in the Stewart textbook, and those are the ones, those you should know. When you see them, you should recognize them, and you should just be able to write them out. Okay, so that handles a couple of things here: trig identities, inspection. So that's one of the strategies that we're going to have. Next strategy, if we've got a product of sines and cosines, there's two possibilities, in fact, in that case. At least one of the numbers is odd. That's a possibility, or they're both even. That's the second possibility. We're going to handle this first possibility first. At least one of the numbers of these exponents, m and n, is odd. So in that case, we are going to proceed as follows. Let's go by example here. Let's check out which one is odd. We've got sine cubed x times cos squared. So 3 is odd. So this one here is odd. Okay, so pick an odd one. So that's what I'm doing. I'm picking an odd one. So this is my strategy. Pick the odd one. Save one factor. I'm going to show you what I mean by that in 2 seconds. Save one factor. Express the rest in terms of the other one. Okay, this sort of slightly cryptic instructions here to the side means this. 3 is odd, so what I'm going to do is save one factor of the sine. So I'm going to write sine as sine cubed. I'm going to write it as sine x times sine squared of x times cosine squared of x dx. So basically that's my idea. Pick the odd one. That was 3. Save one factor. That's that. Then express the rest, that is this here, in terms of the other. So I want to now express sine squared in terms of cosine squared. So I'll do that. That's going to be sine x. And then I'm taking the sine squared and I'm expressing that as 1 minus cosine squared. And then I still have that cosine squared. Perhaps now you can see why this strategy is going to work. And I can now because what I've done is I've set myself up to have the derivative of the cosine function right here. And so I can now make a u substitution. I can let u be equal to the cosine of x, and then du will be minus the sine of x dx. And then that allows me to make the following substitution. Sine x dx is minus du. So there'll be a minus sign, and then there'll be the du. And then I have 1 minus u squared times u squared du. So that's nice. Then I can just write that here. I'm maybe going to reverse the order to get rid of that the negative sign. I'm going to put that in here like that. So then this will be u. I'm going to multiply that at the same time. I'm going to get u to the 4 minus u squared du. I can easily integrate that. 1/5 u to the 5 minus u cubed over 3 plus the constant, and then I do the back substitution and I write out the answer. It is equal to 1/5 u to the 5th. Well, u is the cosine, so this is cosine to the 5th of x minus 1/3 cosine cubed of x plus the constant. Okay, again, of course, check by differentiating. Okay, that's the possibility 1 when you have a product of sines and cosines. Possibility 2, they are both even. Okay, then the idea here is use the half angle identity on both. Identity. Let's try that again. Use the half angle identities on both. So that's going to look like this. The integral sine squared is 1 minus cos 2x over 2, and then cos squared is 1 plus cos 2x over 2. And I multiply that out. Isn't this nice? I get 1/4 times the integral, and then this is it's like factoring a perfect square, just the difference of 2 squares. So I'm putting that back together. This is like that, except that it's 2x, like that, dx. Okay, and then I can go ahead again with the half angle identity, and I get this here. And 1 minus Cos squared is 1 plus cosine 4x all over 2 dx. Okay, and that is this way here like that. Okay, so now my problems are all solved. I can do this quite straightforward. I have to do maybe a little bit of expansion, but it does look like this. Let me just one more step with the integral there. The integrand I can write like this. And that is 1. I can combine that 1.5, and I get 1/2 minus 1/2 cosine 4x dx. There it is. Okay, so easy now to integrate. That is going to be 1/8 x minus sine 4x over 4 plus the constant. Okay, again, check by differentiating. Okay, that's the strategy there for the products of sines and cosines. So identities and possibly separating factors. Okay, let's try another example here. Integrate cosine to the 5th. Okay, I see that this is odd. So it's not quite the exact instructions that I had before, but I am going to write this like this. Cosine squared x squared times cosine x dx. Okay, cosine squared is 1 minus sine squared. That's going to be squared. And then this is cosine x dx. Now I can make a substitution because this here is the derivative of, well, it's a derivative of sine. So I see that I can see this as a composition. So I will do that. I will say let u equals sine x, and that means that du will be cosine of x dx. So my recommendation actually here on this one, I mean right now, would be to stop the video, do it yourself, and then check the thing so that you make sure that you've got the substitution down and things are all good. Always better to do work yourself than watch somebody else do it. It's much better to stop, try yourself, and then have a check. And you know what, if you when you try yourself you realize I'm not making any headway, try for a while and then watch the video and go, oh, I see what I didn't pick up on. That's going to be a much more effective learning strategy. Okay, so here we are. That is the substitution I'm going to use. So then that will look like this. The integral from 1 of 1 minus u squared, because u is sine, and that will be squared, and then cos x dx is du. So there's a nice substitution. It turns the thing into a nice polynomial. Polynomials are like the most beautiful thing on the planet. We can use them to approximate things. They're easy to integrate. They're easy to differentiate. We can find their zeros. They are just dilly deluxe. Okay, so there's integral of a polynomial. So I will quickly integrate that. U minus 2u cubed over 3 plus u to the 5 over 5 plus c. There it is. I back substitute. U is sine x. That's what was my substitution. 2/3 sine cubed x plus 1/5 sine to the 5th x plus a constant. Okay, check by differentiating. Now, okay, so you could check by differentiating. That's a good idea. Let me write that to encourage you to do this. It also makes sure that your differentiating is staying in tip-top condition. But the other thing you can do is check with Wolfram alpha. Now, let's have a warning about this in this case. The answer you get from Wolfram alpha will be correct. But it may look a lot different than what you've produced. So for example, this is a correct solution, but I could put this integral into Wolfram alpha, and what I would look at would look could look quite different, but it will be an equivalent solution. And to go from one of those solutions to the other, you might need to use a whole different number of trigonometric identities. So just like, I could write this, and that would be exactly the same as writing this, even though they look completely different. Similarly, if I have some expression for my answer with the trigonometric functions, and then I check with Wolfram alpha, it may not look at all the same, although it will be equivalent. So just be cautious when you're looking and using Wolfram alpha. You don't say to yourself, oh no, I'm wrong, because you may not be wrong. They may be equivalent. Okay, so that's just a caution there. All right, so other trig functions. Let's have a look. What have we not talked about? Tangent, cotangent, secant, and cosecant. Okay, so we should be able to take the integral of the tangent function. It's a very important function, actually. In fact, also the fact that the arctangent and the derivative of the arctangent 1 over 1 plus x squared is also going to come up a lot. So this is an important one. So what do I do here? I recall that the tangent is the sine divided by the cosine. And then that, once I write it like that, it makes it, I think, much more obvious that I can make a substitution, because the sine is the derivative of the cosine. So I will then let u be equal to cosine x, and that means that du will be equal to minus sine x dx. And that allows me to make a nice substitution here. This then will be minus the integral of du over u. That's easy to do. That is minus the log of the absolute value of u plus a constant. And that is indeed the minus the log of the absolute value of cosine of x plus c. And I can keep going here, minus the log of the cosine. No, I don't want the minus if I'm going to do that. The log of the cosine of x to the minus 1 plus c. Okay, that's the log. These are log rules. Okay, so that is minus log of, whoops, a little too fast there. Minus log of a is log of a to the minus 1. Okay, the log rules. This is how math just kind of, builds up. You get those nice strong foundation. Anything that you're not seeing here, just fill that in. You're going to get the time back. So you want to get everything as strong as possible, so that it's just really easy to add these additional little tactics on top. You don't want the whole foundation to be wobbling on you all the time. Okay, so here we are there, and then that is, I could write that like this. The reciprocal of the cosine function is the secant function, so this is, there we go. There it is. Okay, so first thing I'm storing in my brain is, hey, look, when I integrated a trigonometric function, I actually ended up with the log of another trigonometric function. That's maybe the first time I've seen that. So that might happen with other ones. So I want to be on the lookout, thinking to myself, okay, if I'm looking at one I haven't done before, is there some way that the log of some other trig function is going to come? Because it has happened once, maybe it will happen again. Okay, so indeed it's going to happen again right here, and we're going to see it in actually a more disguised role coming the next couple of integrals. So here I'm trying to integrate the cotangent. I'm going to rewrite the cotangent in terms of sine and cos. Okay, stop the video right now, do that yourself, and make a substitution and go through and see if you can get the answer, and then start the video. Okay, because we're doing a very similar tactic to the one to part A. So if you really carefully followed part A, you should be able to do part B. Why not do it yourself? Okay, so now I'm going to do it. Okay, here it is. Cosine x over sine x. That is what the cotangent is. And then I'm going to do exactly what I did up there. Let u be the sine of x. And that means that du will be the cosine of x dx. And then I can write this then as the integral of du over u, and that is the log of the absolute value of u plus c. Back substitute, this is the log of the absolute value of sine. There it is. Okay. Now I'm going to go to one that is actually not obvious. Do not think that this tactic is obvious. It is not obvious at all. And in fact, this was an unknown problem shortly after the calculus was invented. This was somebody had thought to try this, and a variety of people have tried it and thought, holy, this one's not coming so easily. In fact, you can see this in the history of integration. Some things are very easy to do, and then after a while, somebody will come up with one and say, hey, for some reason we can't do this one. And then it was, in fact, many very well respected and well-known mathematicians would spend some of their time saying, okay, we've got certain integrals we can't do at this point, and think about them. So this one, what falls into that category. So it's not something I don't think it's at all obvious when you look at it, and it was not historically obvious either. So this was Gregory in 1668. Realized how to do this. Okay, we just saw two examples. So one thing would be thinking in thinking. It might be log of something, because we just saw that happen. Could it be? This is some trig something too, not just something random. Could be log of trig something. Okay, so thinking along those lines, and then possibly sort of a problem-solving thing, and then possibly thinking integrals I can do by inspection that may bear upon this problem. Okay, that's something else. So let's just, I don't know, we see the secant here. Let us just write out some that we can do by inspection, just to sort of see what does this help us at all. So I know this, that the integral of the secant function is tangent. What else do I know? That the integral of secant, whoops, not secant squared, of secant x tangent x. I know that not be lazy with my dx's either. I'm a bit lazy sometimes. Secant x dx. There we go. I know what the integral of secant tangent is. That is secant. So I know that. So I now, in the problem-solving model that math can sometimes be like, these are the things I know, and then I'm playing around, I'm trying things, and I'm hoping to make headway. And because I already know how to do this, I'm going to land on the exact thing to do. But that is not the way that these things are done when people are doing them for the first time. If you want, you could stop right now and think to yourself, I'll try this. Like, I'll just use these bits of information and think, can I come up with something? Don't feel bad if you cannot. And then once you see it, you're like, okay, so then that's another little tactic that I have that I might be able to bring to bear on a new problem. So you're kind of collecting up ideas. And here's how we're going to handle this one. We're going to take the integral, there it is, secant x dx, and we are mysteriously, in some sense, going to think, I know what to do. Let's multiply top and bottom by 1, and 1 looking like this. There, that's 1. That's not going to change anything. Multiplying by 1. However, it's a very special form of 1. And I will then write that out. That will be then the integral of secant squared x plus secant x tangent x. And in the denominator will still be that secant x plus tangent x dx. Okay, it doesn't actually look like things have gotten better, but they have, because if then I think to do this, let u equal, now that idea that it might be a logarithm is in my head, secant x plus tangent x, then gloriously look what happens. Du is secant squared x plus, that is the derivative of the tangent, and then the derivative of secant is secant x tangent x. And that allows a very easy substitution. This then becomes the, just as it has in the previous cases, this becomes the integral of du over u, which is the log of the absolute value of u plus c, and then I do the back substitution, and it's there. Okay, a non-obvious maneuver right off the top to multiply by 1 in that unobvious way, but perhaps having these guys sort of in the forefront and thinking I might be a log, you might come up with that, but certainly that was something that took some time for somebody to think of. Okay, now that we've got that idea that we may want to multiply by something, you may indeed want to try something similar here before you see me do it. You might not want to, but I won't know. So the by inspection ones that are in my head are these ones. Cosecant squared x dx is minus cotangent x plus c, and that the integral of cosecant x cotangent x dx is minus the cosecant x plus c. Okay, so the derivative of the cotangent and the cosecant should be known to me. They are known to me, and if they're not, I can figure those out easily. Okay, so now with that in my head, and having just seen the previous question solved, I will go like this, cosecant x, and I will multiply by 1. It will look like this, cosecant x plus cotangent x divided by cosecant x plus cotangent x. So I'm multiplying by 1 again, and I'm doing 1 is going to be represented in a different form. I mean, there is actually, it's quite extraordinary, you know, multiplying by 1 and adding 0. And doing that in a clever way can help you in so many different problems. That's when you think of how you maneuver around. I mean, that's often what you're doing. You're just multiplying by 1 and adding 0, because those two operations do not change anything. But it allows you to see things differently, and then that allows progress. Okay, so here we are, multiplying by 1. And what do I get when I do that? I get here cosecant squared x plus cosecant x cotangent x divided by cosecant x plus cotangent x dx. Okay, now I'm the same idea. I'm looking that it might be the log, so I'm taking the denominator here. Let u be cosecant x plus cotangent x. I'm investigating what that would force du to be, and it's minus cosecant, let's not be lazy here, it's minus cosecant x cotangent x minus cosecant squared of x, which of course I can factor the minus sign out. And I see that, oh goodness, that is good news, because this thing here, oh, let's get the dx on there, and then that whole thing there is just the negative of this here. So that is really good news. So I can then do that substitution. I get minus the integral of du over u, and then I get minus log absolute value of u plus c, and that is minus log of cosecant x plus cotangent x plus a constant. Okay, that is all I really want to say right now about the trigonometric integrals. Let's just make a note of what we've seen, what the ideas we've seen. One, we've seen use trig identities. So those things need to be available to you, trig identities. We've seen sort of, oh, well, let me call it saving one. Saving one. So that is when we have something like this, when we have a product, I don't know, like this, cos to the 5x times sine to the, doesn't matter, time to the 7x. We've seen the idea of saving one, and then we have seen the log function come in, log function, which let's be consistent, the natural log function. We've seen that show up, and we've seen after we saw this come up sort of naturally, then we had the idea of multiply by 1. Smart. Multiply by 1 in a very clever manner. Okay, so these are strategies to allow us to integrate the trigonometric functions. So of course you can keep making these things more and more difficult. For example, I could just say, oh, I got a good idea. What's the integral of sine squared x times, cos to the 5x times, I don't know. Well, they're going to all turn into sines and cosines. Maybe I'm not being so clever, but certainly I could put something on here like this, and then this may or may not be doable. Okay, so this game can get, this game can be difficult, and also what we haven't talked about yet, I don't believe we've talked about this yet, there's no guarantee that there's actually something here. I can't tell on difficult ones by inspection whether there's something here that is an elementary function that actually has this derivative. So you can actually be in a situation where somebody gives you one of these, and you can sit there until, well, pretty much forever, indeed forever, trying all these little tactics, substitutions, or using these trigonometric scales, and then possibly going by parts, and keep going, and you will not, in fact, ever be able to find an elementary function that has this derivative. So that is a bit of a bummer, because you also cannot easily, with the skills that we have, we're not going to even be able to recognize that situation. So we're not going to harp on spending too much time making these things like more and more complicated. What we want to do is get the basic strategies down. Okay, so far we've seen, and that's how I'm going to test this too. I want you to understand the basic strategies. I don't want to, my idea is not going to be to say, let me try to make it as tricky as possible. You have to do integration by parts twice, and then three tricky substitutions, and then you have to remember 4 trig identities, and then you get the answer. That's not my strategy. Okay, what I want you to know is the basic strategies, and so far that is going to be substitution. This is big. Definitely you want to know, you want to be able to see how to use substitutions, and I want you to be able to do by parts. Okay, and I want you to understand that you can use trig identities. That's where we are so far. And I will promise you that I will keep the ones that I ask you how to do to a reasonable level. At least I will think that they're reasonable. Okay, so that is the trigonometric integrals lecture. We'll be back with another lecture in which we're going to use we're going to basically combine these things, and we're going to come up with trigonometric substitutions, and we'll do that next, and then after that we'll do partial fractions, and then we'll have sort of covered the basic techniques that I want you to be solid on in order to be able to integrate. Okay, that's it for now, and I'll see you next lecture. Thank you.